Okay, I got another problem here. So this time I'm going to be doing a StatMech problem from the December 2019 subject exam. And this is problem number one. And the reason I'm doing this problem is because it's going to be slightly related to the previous quantum mechanics problem that I did with the infinite square well. So let's go ahead and get started. So consider a three-dimensional cubic box containing n indistinguishable particles that can either be in the internal volume of the box or observed onto the surface of the box. The box is immersed in a medium with temperature T, assuming that the particles both in the three-dimensional volume and the two-dimensional surface are non-relativistics and obey Boltzmann statistics, meaning they behave like an ideal gas. The box has side length L, and there are N2 particles on the surface and N3 in the volume. So the reason it's kind of similar to the uh, previous quantum infinite square well problem is because the uh, eigenfunctions for the 3D box are going to be just three of those eigenvalues for the infinite square well solution. So what do I mean by that? The particles in the box uh, obey the time independent Schrodinger equation. And the solutions, uh, just like the infinite square well, except this time it's in 3D. So the solution to this equation is just three of those multiplied together, one for each X, Y, and Z. So if the solution to this problem, if you don't know where these comes from, is one of these. So for example, the 1D case for a particle in an infinite square well was this solution here. And now we're working with a 3D box, so that's why we multiply three of them together. And I add the subscripts nx, ny, and z. And the energy of the particle in the 3D volume is going to be uh so this n now is actually these nx, ny, and z combined like this, and the energy of one. So if you think that I'm just skipping too far ahead and writing these down, I basically solved this problem already. Uh, and now we're just going to use those results to do a different StatMech problem. So that's what the energies are. This is what the eigen functions are. And now the first part of the problem is to calculate the canonical partition function for the particles in the volume of the box and the canonical partition function for the particles on the surface. Okay, so one more quick thing I'm gonna do to set up this problem is I don't really like the notation, so I'm gonna call N3 NV for the particles in the volume, and N2 is gonna be NS for the particles on the surface. I just think that's slightly better than what they use here. It makes more sense to me. Okay, so now the uh, partition function for one particle in the, well, for a particle anywhere is equal to the sum of all of the possible energy eigenstates in an exponential divided by t, like this. So this is for one particle, and then later to get the partition function for all the particles, because they're identical, there's going to be uh, a quick, simple. Uh, so later we're going to use this formula here, but we'll get to that later. So we just have to plug in now for the 3D case. So one particle in the volume is going to have a partition function that looks like this. It's a negative sign, and then I'm just plugging in this formula here. And then remember that this sum over n is actually a sum over three different indices now. So I guess I have to rewrite that. Okay, now the next step is to assume that when okay, so if you look at this formula again here, so the possible energies are, these nx, ny, and z, they increase by integer values, just like they did before with the infinite square well. So one of the energy levels could be nx equal to 1, nx, ny equal to 1, and z equal to 1. And then you plug that in here, and you would just get, h bar squared divided by 2m pi squared L. And then all this would just give you 1. And then, the next energy level, you could change one of these from 1 to a 2. And what we're going to assume is that when you go from one energy to the next, so the change delta En is going to be much less than tau, which is in the denominator here. So we're going to assume that energy spacing of adjacent levels is small. compared to tau. And what this means we can do is we can treat these sums and convert them into integrals. And that's going to make this problem a lot easier. So let's go ahead and do that. Z1 volume is equal to integral from 0 to infinity dx, oops, dy, z. And then we still have this exponential factor here. Okay, now one thing that I'm going to do is I'm going to define a constant called alpha that's going to encapsulate all these other constants that don't are not we're not integrating over. So we only are integrating over nx, ny, and nz. So all this other stuff we can pull out and define just the therefore alpha squared is squared like that, and that's just gonna clean this up a lot. Have a negative sign here. Okay, so that's nice. And now what we see is that this exponential can actually be separated, and this is really just the same integral three times. So if we separate the like that, that's one of the integrals, and we separate the y and y. And like I said, this is just the same integral three times. These nx, ny, they're just dummy variables. So we can call them all just dnx. And then we have the same integral dnx. And we're just going to cube that like that. Okay, so now this integral, usually it will be either on the formula sheet of the subject exam, or if you're just practicing, you can just use integralcalculator.com or something like that. So this turns out to be pi 2 alpha, and then all of that is cubed because we're cubing. So the partition function of one particle in the volume looks something like this. And let's see what the problem wants exactly. Calculate the partition function for all the particles. So we still have to use that other formula. Uh, yeah, and now we can convert back to the standard stat mech variables like T and L instead of this alpha. So if we do that, we get so that's 1 over alpha. Cube that. Just doing some algebra here now. This gives you 2 to the 3 halves, m to the 3 halves, L to the cube. That's good. That's volume times tau 3 halves, h bar cubed pi cubed. Okay, this looks like a mess, but we can still simplify this. 8 is actually just 2 cubed. So what does this give you? We have 1 over 2 to the 3 minus 3 halves, m 3 halves. Okay, so this L cubed, that's volume, so that's nice. Can write volume there. We have I 3 minus 3 halves, and we have h bar cubed. So we have a lot of stuff to the 3 halves power, which is kind of weird, but it's okay. So we have volume up top, then we have 2 pi h bar squared divided by m tau, and all this is to the 3 halves power. So there you go. That's partition function for one particle. It's not very, you know, pretty looking thing, but it's what it is. And right, so before we find the partition function for all the particles in the volume, let's now quickly find the partition function for the particles on the surface. So we had the volume, and now the partition function for one particle on the surface, which I'm going to use S here, um, is going to be the exact same thing, except we only have 2 dimension this time. Obviously, the surface is 2D, the volume is 3D. So what that means is we're going to have only dn x and dn y to integrate over. Or what it also means is that instead of cubing it here, because these integrals are going to be exactly the same, we're just going to square that integral. So we can really just copy exactly what we had up there for the volume partition function. And now instead of cubing it, we're just squaring it because we're working in 2D this time. And I'm gonna skip all the algebra. Okay, so this, oh, maybe so this was gonna give you the same answer here, pi to alpha squared this time, and that's gonna give something like this. And now one small important detail. So this L squared is equal to the area. So if we want to write in a similar format to this, we're going to have A over 2 pi h bar squared divided by m tau. And then if you did it like the way I did it here, one thing you have to remember is that there are so the cube looks something like this. And obviously there's six surfaces, there's six sides to the cube. So what we found was the partition function for particle on one of the surfaces. So we just found uh, this is X, this is Y, and we just found all the possible uh, um, energies within a 2D surface. So basically where I'm getting with all this, there needs to be a factor of six here. And this is just because there's six sides of the cube. You could have added the six anywhere um, you wanted to, like just out here instead. But that's what random factor of six comes from. Okay, so we have the single particle partition functions, and like I said earlier, we're dealing with indistinguishable particles, and so just a simple formula that converts the partition function of a single particle to the partition function of all the particles if they're uh, when working with identical particles like we are. So if we want now the partition function of all of the particles in the volume, so I'm gonna write that just ZV, all the particles in the volume is equal to 1 over uh, particles in the volume. So remember some of the particles, so there's n total particles and some of them are in the volume and some of them are on the surface. So times the partition function of one particle in the volume to the NV like that. Oh, and this should be factorial here. Yeah, okay. So that's equal to just plug in what we found for this here. B and doing something very similar for the partition function of the particles on the surface. It's gonna look almost exactly the same. Here we have six uh, area, 6 times area. And this factor is just to a different power, like that. So that's all of the first part. Calculate the canonical partition function for the particles in the volume of the box and for the particles on the surface. So did that. Okay. So that was all part A. Part B, for a given T, N, and L, find the expression for the numbers of particles in the volume. At one temperatures are most particles in the volume. So to do this next part, we're going to have to use the chemical potential. So there's a couple more little useful formulas. In general, the single particle partition function can be written in terms of something called the quantum concentration. This is from uh, Cattell. Um, StatMech textbook by the author name of Cattell. That's typically used in undergrad statistical mechanics, but nevertheless very good book that I highly recommend. And we can also define another quantity here, little n, which is just the density of the particles. So, for example, in the volume, we have the so NV would be the number of particles in the volume, and NS would be the number of particles on all six sides of the cube, like that. And the reason I'm doing all this is because the chemical potential now, uh, which this formula is from the same textbook again, is equal to tau ln little n divided by the quantum concentration, like this. And now we're just gonna rewrite this using these equations to get it in terms of, ns and the single particle partition function. So first thing we do is plug in n. So n is, uh, you know, okay, so we need to do this separately for each. So the chemical potential inside the volume is equal to tau ln NV. Should rearrange this. Well, I'll do that in the next step. So NP is capital NB divided by V, and the rewrite this and solve for NQ is equal to Z1 divided by V. If we're talking about the volume, this is Z1V. And this is in the denominator, of course. So this is okay. So then we see that the volume cancels out and we're left with NV over Z1V, like that. We're going to do the exact same thing with the chemical potential on the surface. There's a mistake here. Oh, okay. Doesn't matter. This, you can put this factor of 6 here or not. It's 6a, and then the quantum concentration for is again going to be 6a divided by C1. Oh, yes. So either way, these um, factors will cancel out. And you get that the chemical potential is just like that. Okay, so they look almost identical. Uh, just, yeah. Okay. Now the last key part in this problem that you have to know is that uh, the uh, particles obey Boltzmann statistics. They behave like an ideal gas, which means that the box should always be in thermodynamic equilibrium. So if there were uh, a really large amount of particles on the surface, they would just slowly go to the volume and vice versa. What that means in terms of these two equations is that the chemical potential in the volume is equal to the chemical potential on the surface. And that's because of thermodynamic. So that's how we're going to relate the number of particles in the volume to T, N, and L. So if these two are equal to each other, we have uh, T, L, N, N, V, 1, C, B. We can cancel these T's out and uh, exponentiate both sides, and we're left with NV 1 like this. Now we need to plug in the single particle partition functions again, which we solved for earlier. Gonna quickly rearrange this so that we have the partition functions in the numerator, not the denominator. So okay. So these are almost exactly the same. One has power 3/2, one just power 1, and this one has a factor of 6. So we have uh, E. Like this. Okay, so you see that I already rewrote A again as terms of as L squared, and V I'm gonna write as L cubed. because now a lot of this stuff is going to cancel out, like the L squared over there. This is going to take away one entire factor of this, so we're left with 1/2 there. So we have 1 over NV L is equal to MT. That almost done now. The total number of particles in the volume and surface is a constant, of course. So, and we're solving for the number of particles in the volume. So we're just gonna solve this for ns is equal to n minus nb, and then plug that in. So let's see. NB is equal to NS. Oops, I lost a factor of 6 somewhere. This should be a 6 here still. Yep. Okay. So L is 6. Like this. Okay, then we just plug this in here. Okay, now we just have to solve for NB. Okay, so there's the final answer. The number of particles in the volume in terms of L, T, and N. Just like the problem wanted. And now let's see at what temperatures are most of the particles in the volume. So if we look at this, where is it? So there's the answer. And see that as T gets bigger and bigger. So if um, basically as T goes infinity, you have this term here gets really, really large. Plus 1 is basically just this term. So you get that these two terms cancel each other out, and you're left with NV goes to N. So as you increase the temperature more and more of the particles are going to be in the volume of the cube instead of on the surface. So yeah, that's it. Thank you very much for watching. I hope this problem was useful. Yep.